Given the model in the previous video, we can actually find the discrete Fourier transform of the x-axis here by setting the y-axis to cosine waves of multiple frequencies and then find the dot product each time. In this case, here's a cosine of 1 hertz. Look at the dot product, which is the middle of the cross convolution here. You can see it has a frequency component of 0 because it's a constant. But instead of having to do this for cosines of all these different frequencies, why not instead keep it fixed at 1 hertz and then find the diagonal sum of different slopes? For example, here's a slope of 1, find a slope of 0 for the 0 hertz component, 2 hertz, 3 hertz, and so on. And you notice that these diagonals sometimes overlap. Here you can see that for each cell, for some cells, there are multiple frequencies that it contributes to. And not only does and this optimizes the process, we can actually optimize this further by only going through half the waveform and then modulating back and negating it, shown here. So then you can find the area of those cells and then add them or subtract them based on their sign, or based on their color in this case. But then we can optimize it further by going through a fourth of the way and then going back down, because the hump of a cosine wave is pretty symmetrical around the middle. We can move that back down. So then we only need to find the area of these cells. And then we can optimize it even further by permuting the columns or the x-axis samples as such. And then in this case, you only need to find the area of these cells. And you notice that in some cases, you can find the area of rectangles instead. And then you can use these intermediate rectangles, add them, find the sum or find the difference, saving a lot more time. And these optimizations are the essence of the fast Fourier transform.